Hello and welcome to this new Stable Diffusion fine-tuning tutorial. This is an updated and more comprehensive guide for training new concepts in Stable Diffusion. So if you want to generate great images for custom objects or styles, this tutorial is for you. I will be presenting different training methods and discussing their pros and cons, and by the end of this tutorial you will have a better idea on which method to use and for which task. And if you have a low VRAM machine like myself, you can also follow this tutorial. I will show you the different settings you need to adjust so that you can run the different methods. Okay, so in the first part of this video we'll discuss the different fine-tuning or training methods from a theoretical point of view, to have a better understanding of how each method works under the hood, and then I will show you how to perform each method using the different public user interfaces available online, and I will also show you how to generate good results using each one of them. And finally we'll compare the results obtained from the different methods, and I will share with you different tips on how to improve the images you generate. Okay, so let's not make this video longer than it should be, and let's start right away, but of course feel free to skip the part you're more interested in. So first we'll start by understanding the differences between the four techniques that we're going to use, which are Dreambooth, Hypernetworks, Textual Inversion, and low rank adapters, or LoRA for short. And let's start with the Dreambooth technique. So Dreambooth is arguably the most famous training method for Stable Diffusion, and generally speaking it produces the best results. It was first developed by Google to personalize text-to-image diffusion models, and it achieves that by embedding the object or the subject we're training on in the output domain of the model via a unique identifier known as the instance token. Okay, so here we have the Dreambooth training loop, and by the way this training loop is actually very similar to the training loops for the other techniques, and you'll see that later on this presentation. So to understand what's going on here, let's follow the prompt, which is the text on the left side here, on its journey through this illustration. So in the first example we're training a Stable Diffusion model on a specific kitten that we're calling here MLWH kitten, and this is the unique identifier that we talked about, which should be chosen carefully, and that's because we don't want to choose something that is already known to the Stable Diffusion model. So for example, if we choose here the token Berman as the unique identifier, which is by the way the name of a well-known cat breed, this would mess up the understanding of the Stable Diffusion model, and anytime you want to generate a random Berman cat image, the fine-tuned model will generate an image of the specific cat you trained it on or you fine-tuned it on, and as such it would lose the ability to generalize. So I hope this point is clear for you. So that's why you need to choose this instance token very carefully. So the next part in this training loop is to generate the embeddings for the prompt, which are simply a vector representation for each token in some high-dimensional space. And then both the embeddings and a random noise or an initial random noise image will be passed down to the Stable Diffusion model, which will generate an image based on the description that it received from the prompt. And once the image is generated, it is then compared to the training image and the loss is calculated. And as a final step in this loop, the loss will be used to update the Stable Diffusion model weights. So this is actually the first part of the training loop, because as you can imagine, when training using only the images you've provided, this could lead to overfitting or something that we call a language drift, meaning that the model would generate images of this specific kitten even when asked to generate images of random kittens. And to resolve this problem, Dreambooth uses a technique called prior preservation loss. And as you can see here, this prior preservation loss is an additive loss that acts as a regularization factor to prevent the language drift issue. So here we have a second prompt, similar to the first one, but without the unique token. It is used by a frozen copy of the Stable Diffusion model to generate images of random kittens. So these images are referred to as class images, and they serve as a second training set. And then the prior loss is calculated and added to the initial loss, and then they are both used to update the Stable Diffusion weights. So this is basically how Dreambooth works, and I hope that's clear for you. Let's move on now to the second technique, which is the textual inversion. So the textual inversion is actually an embedding training method. It is used to make Stable Diffusion models learn the embeddings of custom objects or styles through a unique token as always, which we refer to as the instance token. And as you may have noticed from this training loop, we have a very similar loop as for the Dreambooth without prior preservation. So let's not focus on the shared steps. But the main and the most important difference here is that the loss is used here to update the embeddings instead of the model weights, and that the model itself is frozen, so we only use it in the forward pass. And to better understand how updating the embeddings would make the Stable Diffusion model generate images for the custom object, you can imagine that the new embedding is like a combination of embeddings that describes the unique features of the object that we're training on. So for example, in this case, here we have the MLWH kitten, which has white body fur with a gray patch on its head, and this is an identifying feature for this specific kitten, along with other features like its eye color and its size, etc. So when training, the new embeddings can be imagined as some sort of a combination of embeddings that describes these specific features, which are already known to the original Stable Diffusion model. And that's how the Stable Diffusion will be able to generate images for specific kittens without the need to train the model itself. So I hope that makes the idea behind textual inversion more clear for you. And by the way, if you're interested in more details, I will leave the links to the different papers for the different techniques in the description, and you can check them to better understand and to have a deeper understanding of these techniques. Okay, so let's now move on to the next method, which is the Hypernetworks. So the Hypernetworks are neural networks that are trained to act upon the input of the cross-attention layers to make it understand and be able to generate new concepts. So as you can see here, for Stable Diffusion models, we always start with a noise image or a random noise image, and the component that is responsible for denoising this image to generate an output image for the prompt is called a U-net. It is actually a type of an autoencoder with a U-like shaped architecture, hence its name U-net. So this U-net uses layers called cross-attention layers, which takes as input three different variables: the query, the key, and the value. And the Hypernetworks that we train acts on these three inputs and modify them to make the model generate images for the chosen subject. So in this illustration, the cross-attention layer are represented with the hyperplanes, so the training loop is always the same except for the additional hypernetwork, which is, by the way, an MLP or a multi-layer perceptron. So also here we have the Stable Diffusion model frozen, and the loss is used to update the hypernetwork weights instead of the Stable Diffusion weights. And that's actually how this method works. I hope it's clear for you, and let's now move on to the final technique we're going to use, which is low rank adapters or LoRAs. So the LoRA is a training method originally developed by Microsoft for LLMs or large language models to accelerate their training process while consuming less memory. And as we can see here, similar to the Hypernetworks, the LoRA acts on the most important part of the Stable Diffusion model, and that is the cross-attention layers. However, the main difference here is that the LoRA method fine-tunes the weights of the cross-attention layers by injecting new weight matrices that are trained on the new objects. So as you can see here, the whole model is frozen except for the cross-attention layers, and that's how LoRAs work in a nutshell. So I hope you have a better understanding now of how each method works. And the main takeaway from a practical point of view is that these different techniques use the same type of inputs. So to be able to run any one of them, you need training images, prompts, and a Stable Diffusion checkpoint. And they also have similar outputs, some sort of file, and a unique token. So for the Dreambooth, the file would be a Stable Diffusion checkpoint, an embedding file for the Textual Inversion method, a Hypernetwork weights file for the Hypernetworks method, and of course a LoRA file for the LoRA technique. Okay, so let's now compare these methods based on some attributes, but please keep in mind that these are based on my own observations and my own experience with each method. And also here, for example, if I say this method is fast, meaning that it is fast compared to the other methods. So the first one here is the training speed. So the Dreambooth is the slowest, and that's expected since we're training the whole Stable Diffusion model. The next attribute is the file size, and we can see that all the methods except the Dreambooth are very portable and can be shared easily. However, we can see that the Dreambooth provides the best results, the Textual Inversion and the LoRa's generate good results, and the Hypernet comes at the last place. The next attribute is the compatibility, and by that I mean whether the method is able to produce good results when combined with the other techniques. And for example here, the Textual Inversion works well with both Dreambooth and LoRa's, but not so well with the Hypernets. Then we have the weighting, which refer to the ability of assigning weights to either the model or the instance token. And we can see here that we can apply some sort of weights for the different techniques. And finally, the object or style attributes. And what I mean by that is whether the method works better when trained for objects or style. And from my own experience, to train a new object, I would rather choose Textual Inversion rather than Hypernets. But again, this doesn't mean that Hypernets are bad for training objects. It just means that they perform better when trained for styles instead of objects, and the inverse is right for the Textual Inversion training method. Okay, so let me now show you quickly some numbers regarding the training duration before we start with the practical guide. So here I trained all the methods using the same training parameters on 6 GB of VRAM and 16 GB of RAM, and these are the results. The LoRa was the fastest method to train and the Dreambooth was the slowest. And you may have noticed that I've said above that the Textual Inversion and the Hypernets are faster than LoRa's, and that is actually true because the Textual Inversion and the Hypernets can be trained using half the steps used for LoRa, and as such you would have them trained faster. However, in this comparative table I wanted to use the same parameters so that the values can be compared. Alright, so enough with this presentation and let's start training right now. So in what follows, we'll mostly be using Automatic 1111 Web UI to run and to train the different methods that we presented. But we're going to need to use another Web UI to train LoRa's. And that's because for the time being, the latest version of the Auto 1111 with the Stable Diffusion Dreambooth extension has many issues regarding training LoRa's, and I can confirm from my own experience that training LoRa's doesn't work properly. And what I mean is that after training, the instance token that was used in the training process doesn't produce the intended image of the object or the style. So it is as if the LoRa file that was produced wasn't even trained in the first place. And that's why we're going to use the Koya SS Web UI, which uses a different implementation of the Dreambooth and the LoRa training process, which works fine and produces great results as for the time being. Okay, so let me show you first how to install both user interfaces. So the easiest and most simple way to install Auto 1111 is through this launcher by Empire Media Science. So we simply need to go down and follow the steps of this installation process. The first thing we need to do is to download the latest release and download this file over here. Once you download it, you can simply execute it and it would install the launcher in the folder you select. And after the installation of the launcher completes, a folder will pop up containing the installation files. And before using the launcher to install the Auto 1111, you need to verify that you have the Git installed because the launcher uses it to clone the repository needed. So to do that, you need to open a command prompt as such and execute the git version command. And if you have a certain version returned, that means you have the Git installed within your machine and you're ready to finish the installation of the Web UI. But if your machine doesn't recognize the Git command, you simply need to go to this website, gitcsm.com, and download the Git installer for your version of Windows or Mac or whatever OS you're using. And once you have Git on your machine, you can start the launcher to install the Auto 1111 Web UI. So for the first time you run the launcher, it would verify that you have Python 3.10 installed, and if not, it would install it itself and add it to the path, which is needed for the second Web UI we're going to use. But then you have this Auto 1111 Web UI launcher, and here you have some options that you need to select in order to run the Web UI using specific flags. So I would recommend that you check the Auto Upload Web UI option, as well as the Auto Update extensions. And if you have low VRAM, you can check this low VRAM option and also enable the Xformers. And once you have all the needed options selected, you can simply click on Launch Web UI, and that would start the process of installing the dependencies or the requirements, as well as the Web UI itself. And it will also ask you if you want to install the basic Stable Diffusion 1.5 checkpoint. And I would recommend that you do that because we're gonna need it afterwards. So it's gonna take some time, but in my case it would only take a few seconds because everything I have is installed and up to date. Okay, so this is the Auto 1111 user interface. And before we move on to the next user interface, you just need to install the extension for the Dreambooth. So you go over to the extension tabs, and then from the available you simply load more and search for the Dreambooth extension, and it would show up for you here, but as I have it installed, it won't pop up. And you simply need to click on install on the right side, and then you can verify that it is installed within the installed tab for the different extensions you install. And if you can't find it here in the installed tab, you simply need to go to the settings and reload the user interface so that the user interface would load the new extensions. And as you can see, a new tab would be added called Dreambooth, and in this tab you can train Dreambooth checkpoints as well as LoRa's, and we'll be using this extension to train Dreambooth. Okay, so let me show you now how to install the second user interface, which is Koya SS user interface. So you need simply to access this repository, and we have here a simple installation guide. For the pre-requirements for Windows, you need Python 3.10, as well as Git and Visual Studio Distributable. So after installing the Auto 1111, you would have both of the Python 3.10 and the Git installed in your machine. You can install the Visual Studio Redistributable, and then all you need to do is to copy this command to clone this repository on your machine. So go ahead and click on this button to copy this command, and create a new folder where you want the user interface to be installed. And within this folder you can open a command prompt using the cmd command, and then pass the git clone command. Once it is cloned, you would have this folder called Koya SS. And to finish the installation, you can either copy the next commands in the same command prompt, or you can open the setup.batch file manually from the Koya SS folder, and you can find it down here. So we simply open this setup file, and we have 6 options. We need to run the first option to install the GUI, and for that we have 2 options, either to choose the Torch 1 installation or the Torch 2. The Torch 1 installation is more stable, but the Torch 2 installation is much faster for the training process, but it has some bugs and some issues. I've tested the Torch 2 installation and I've only encountered one problem, and I will show you how to fix it. So feel free to choose the Torch 2 to be able to train LoRa's much faster. I wouldn't choose any option here as I have the GUI installed. So after the installation is finished, you're set to go and you can run the GUI. But if you have an NVIDIA card of the 30 or 40 series, you have another option to install the CUDNM file to make the training process much faster. And you can download the required file from the link provided in the repository. And then you need to choose the second option to install the CUDNM files. And after that, you can simply start the Koya SS GUI using the 5th option. And the first time you run it, it would take some time to install the required dependencies. And here we go. So this is the Koya SS GUI version 21.7, which we'll use afterwards to train LoRa's. So before we move on to preparing the training images, if the buttons on this user interface doesn't work, you simply need to uninstall and reinstall the Fast API and PyDantec libraries, and I'll leave the different commands to do that in the description. Okay, so now let's move on to preparing the training images. And for the training, we need at least 10 good quality images of either a style or an object of your choice. And from my own experience, 30 images produces decent results. And remember that the results you will get depend heavily on this step. So if you use low quality or blurred images, it's going to tax your results pretty heavily. Alright, so in this tutorial we'll be using my own images. So as you can see, we need images with different facial expressions. with different backgrounds and with different clothes. And if you only have small resolution images, you can use the Auto 1111 upscaler or an online upscaler to enhance your training images. So here I have 31 images of myself, and as you can see they are in different aspect ratios and different sizes, so we need to resize them all to 512 by 512, and that's a requirement for training on a Stable Diffusion 1.5 model. And you can use 768 by 768 if you're using a Stable Diffusion version 2. So you can do the resizing and cropping on any image editor software. But if you don't have one, you can simply use this website called VRAM.net, which provides a simple and fast tool to resize multiple images quickly. So you simply need to upload all the images here. And then on the right side you can set the width and height as well as the ratio. And before saving a zip file, you can set a name pattern. So for example here, I chose Hamza 512-X, and the X will be replaced by the number of the image. And finally you can tap the save as a zip file, and it will generate a zip file containing the different resized and cropped images. And here we have the pre-processed images. One last thing we need to do is to generate captions for these training images, and you can do that either manually or automatically using blip or deep borrow captioning within the Auto 1111 web UI. So to do that you simply need to go to the Train tab and then the pre-process images, and here you would need two folder paths, one for the input images and one for the output images, where it will save the images along with their captions. So feel free to create a folder for the images with captions, and once you have set both of the folder paths, you can set the image sizes and then choose the captioning option. So you can use the blip option if you have images of real objects or artistic styles, and you can use the deep borrow option if you have images of manga or anime style. And then you can simply click on pre-process and it will start automatically generating captions. So as you can see here, the different images are added to this folder along with their captions. And for example, for this image we have the caption of a man with a beard and a pink shirt is looking at the camera and is staring at the camera. And feel free to correct and to make the caption as accurate as possible. Okay, great, so now we have prepared the training images and we can start training right away. So the first fine-tuning technique we'll try is textual inversion, and we will train new embeddings for the instance token MLWH, which will refer to my own image. And before we start training, we just need to adjust some settings to optimize the training process and to make it faster. So we simply need to go to the settings tab, and in the training options we simply need to select the move VAE and click to RAM when training if possible, which will optimize the VRAM usage. And we will also need to select the save textual inversion and Hypernet settings to a text file whenever training starts. And finally we need to check the use cross attention optimization while training. And that's it for the settings. Simply apply these settings and feel free to reload the user interface. And now we can start training new embeddings. So the first thing to do is to select a Stable Diffusion checkpoint to use. This is the model that we will use to train new embeddings, and I would recommend that you select the basic Stable Diffusion version. And in this case I'm using the version 1.5 pruned checkpoint, and you can download that from the Stable Diffusion Hugging Face repository. So you can simply search for the Stable Diffusion v1.5 pruned Hugging Face and you would have this repository, and within the file and versions you can find the version that I'm using, and you can download it using this button over here. So once we have selected the Stable Diffusion checkpoint, we simply need to select a name for the embedding, and this name is actually the instance token, so choose it very carefully. Next you can leave the initialization text as is, and for the number of vectors per token there is a general rule of thumb. So for less than 10 training image you can choose either 2 or 3 vectors per token. For images between 10 and 30 you can choose between 5 and 6 vectors per token. And if you're using 40 to 60 training images, you can select 8 to 10 vectors per token. And for 60 to 100 training images, you can select 10 to 12 vectors per token. And if you're using 100 or more training images, feel free to select 12 to 16 vectors per token. So in this case, I'm using 31 images, so I'll be selecting 6 vectors per token. And you can simply then click on Create Embedding. And then you can go to the Training tab and select the embedding you just created. And if you don't find it here, click on the refresh button on the right. Then you can leave the embedding learning rate and the gradient clipping options as default. And for the batch size and gradient accumulation steps, you can select higher numbers, but keep in mind the rule that the product of these two numbers shouldn't exceed the number of training images you're using. So for example, if you have 30 training images and you selected 15 batch size, you shouldn't exceed 2 gradient accumulation steps. So, and that is of course if you have high VRAM, but in my case I'm using 6 gigabytes of VRAM, so I'll keep the batch size at 1 and the gradient accumulation steps at 1. And then for the dataset directory, you simply need to copy the path to the images with caption folder, and then you can leave the log directory as default. And for the prompt template, you can choose one from the different options available, but you can also create your own prompt template, and I'll show you how to do so. So you simply need to head over to the Auto1111 directory, and from there you need to access the Textual Inversion template folder. And to create a custom template for training textual inversion on a custom object, simply open this subject file words and create your own prompt. For example, here I'm leaving the first prompt, which is a photo of a name, file words, and you can modify it as you prefer. So here I have an image of a name, file words, and then you can save it and call it whatever you want. So for example here, custom template, and save it within the current directory. So the name here would be replaced with the name of the embedding, which is the instance token, and the file words would be replaced with the caption of the different images, and this template would be used in the training process to generate images. Okay, so now we can go back to the user interface and refresh the prompt template list. And then you can find your custom template here and you can select. Next, you need to set the image sizes you're using. So if you're using a Stable Diffusion version 2, you need to change these sizes to 768 by 768. But in my case, I will leave it at 512 by 512. And for the max steps, you can simply use 100 steps for each training image. So in this case, we have 31 images, so we're using 3100 training steps. And since the generated embedding files are very small in size, we can save a copy of the embedding each 50 steps. And we can then also compare the different results from each embedding checkpoint, and you can choose the best one to use. So moving on to the next options, we simply need here to check the shuffle tags by comma and to select a low dropout rate to add some regularization to the training process. And for the sampling method, feel free to choose either deterministic or random, but don't keep it at once, it would mess up the training process. And I found out that the deterministic option is much better when training for objects. So we're going to choose here the deterministic option. And finally, you can click on Train Embeddings and the training would start. So the training advancement would show up over here, but I won't start the training now as I'm recording and it would take forever to train embeddings. But once the training finishes, you can simply go to the Auto1111 directory and access the Textual Inversion folder, and then access the folder for the current date, and there you would have a folder named with the embedding that you've chosen. For example, here I've trained an MLWH-TI embedding, and you can find the embeddings files over here. And to be able to use them within the Auto1111 user interface, you need to copy them and then go back to the root directory of the Auto1111 user interface, and then you would have to pass them within the embeddings folder. So once you have the embedding file here, you can use it within the user interface. And as you can see here, I have different files for different training checkpoints. So for example, I will show you now the results that we can obtain using this MLWH3000 embedding. So we can create a simple prompt to generate a simple image to check whether the training process was working correctly or not. And you can play with the different settings here, but I will show you how to do that later on. So let's generate a simple image. Okay, so this is the image generated using Textual Inversion. Alright, so that's fine. It's not a great result, but we'll move on to the other technique, and I will show you how to improve the image generation quality afterwards. So next I will show you how to train the Hypernetworks, and basically we have almost everything prepared for training the Hypernetworks. We simply need to go over to the training tab again and to the create Hypernetwork, and we need to choose a name for our Hypernetwork, and this would work also as the instance token. So here I will choose the MLWH.net token, and for the rest of the options you can leave them as default, but you can also modify a little bit the layer structure of the Hypernetwork. So these numbers describe the number of units per layer within the Hypernetwork. So for example, here within the second layer or the hidden layer we have 2 units, and you can increase that to 3, but that would increase the duration of the training process. But you can leave it as default and it would generate decent results. I would recommend that you do not add layer normalization because it would mess up the training process sometimes, but feel free to use a little bit of dropout if you want some regularization for the training process. And then again, you should go to the training tab and select the Hypernetwork you just created. After that, you can leave the same parameters that you've used for training the embeddings, and everything should work fine. So then you can simply click on Train Hypernetworks and the training should start. And once the training finishes, you can find the training file within the Textual Inversion directory. So you would find a Hypernetworks file with the different saved checkpoints from the training process. And to use these Hypernetworks, you need to copy the files you need to use and paste them within the Hypernetworks folder within the models folder. And to use the Hypernetworks in the user interface, you simply need to click on the Show and Hide Extra Networks button, and then from the Hypernetworks tab you can select the Hypernetwork you want to use, and it would be added to the prompt. So you can copy the name of the Hypernetwork as it is the instance token, and you can use it within the prompt. And by clicking on Generate, you can see a simple image generated. And as you can see, the accuracy is lower than the Textual Inversion, but I'm okay with these results for now. So let's now move on to training our Stable Diffusion checkpoint using Dreambooth. And to do that, we will use the Dreambooth extension that we've installed earlier in this tutorial. So the first thing we need to do is to create a new checkpoint. So we start by selecting a name for the checkpoint, and this is not the instance token, so feel free to choose a generic name. I will use MLWH Dreambooth, and then you need to select a Stable Diffusion checkpoint that will be fine-tuned, and I will be using DreamShaper version 7 in this tutorial. And to download custom checkpoints, you can do that from this website called Civit AI, and over here you can search for DreamShaper and you can download it, and you can find different checkpoints with different styles. And here you can also find Textual Inversion, LoRA and Hypernetworks. So this is the DreamShaper version that I'm using, and to be able to use it within the user interface, you should save it within the Stable Diffusion folder within the models folder. And by the way, every Stable Diffusion checkpoint should go there to be able to access it within the user interface. So once you selected the source checkpoint, you simply click on Create Model, and you should wait a little bit for the model to be created and selected, and then the settings option will be active and you can choose the different settings for the training process. So the first option is the LoRA option, and it should be used if you're training LoRAs, but as we've discussed earlier, it doesn't work, so we're not going to use it now. For the training steps per image, as I said earlier, 100 steps per image is fine, so feel free to leave it at 100, but if you want the training process to be much faster, you can lower it to 80 or 70 steps per image. It would lower a little bit the quality of the produced images, but it would train in a much faster time. For the pause options, I would recommend that you leave them as zeros. And for the save model frequency, feel free to choose a low number if you have a lot of free memory, but keep in mind that each checkpoint takes about 3 to 4 gigabytes of memory. So for the next option, save preview frequency, I would recommend that you set it to 0, because it would mess up the training process and it would generate errors that would stop the training process. Okay, so for the batching options, as we discussed earlier, feel free to use higher batch size and higher gradient accumulation steps, but keep in mind that the product should not surpass the number of training images. And for the next two options, if you have low VRAM, make sure to check them. And for the learning rate scheduler, it's better to use a constant learning rate, so make sure to select the constant learning rate option. And then for the image processing, make sure to select the correct size, so 512 for 1.5 Stable Diffusion version and 768 for the version 2 of the Stable Diffusion model. And next, for the optimizer, you should choose the 8-bit ADAM-W and the FP16 mixed precision, as well as the Xformers option for the memory attention. And as a last option for low VRAM users, make sure to uncheck the cache latents, and then you can leave the rest of the options as default. Okay, moving on to the concepts now. So here we're gonna create the different concepts we're gonna train the Stable Diffusion checkpoint on. And as you can see, it supports training over multiple concepts, but we're going to train over only one, and you can repeat then the same process for the different concepts you want to train on. So for the dataset directory, you can choose the images with or without captions, but if you're going to choose the images with caption, you should modify the caption, such as each caption contains the instance token of your choice. So for example, here I should add the MLWH instance token within each caption in this folder. But feel free to use the dataset without any caption, and after testing both methods I found out that there is not much difference, so that's why I'm choosing here to use the dataset without captions. And then for the classification dataset directory, you can leave it empty. It would be created automatically later on. Next, for the instance token, you simply need to enter the instance token you're going to use. And for the class token, you should choose the class that better describes the object you're training on. And in the instance prompt, you can simply use a prompt that includes the instance and the class token. And for the class prompt, you simply remove the instance token and use the same prompt. And then you can also add some negative prompts, for example, deformed, ugly, and blurry, etc. But they are optional, so you can also disregard them. Then, as we're not going to generate sample prompts, you can leave the sample prompts option as they are, and you can set the class images per instance token as 1, and this option would generate one image or one class image per one training image. So for example, here we have 31 training images, so it would generate 31 classification images. Use it for the prior preservation we've talked about at the beginning of this tutorial. And these are images of random man, which would act as a regularization factor for the training process. And then you can leave the remaining settings as they are. And that's how you define your concept. So I will show you now where to find the classification dataset directory once it's created. And it will be created once you launch the training process. So you can simply go to the Auto1111 directory. And then within the models and within the Dreambooth, you will find a folder for the Dreambooth model you've just created. And within that folder, you will find the classifier 0 folder containing the classification images along with their captions or their prompts. So here we've chosen image of a man as a classification prompt. So each of these images are generating using the same prompt, which is image of a man. And that's how you define the first concept, and you can add multiple concepts or up to 4 concepts using this extension. Then you can modify a little bit the saving options. You can copy the same options that I have, or you can add different options as you prefer. And then in the Generate tab, you can generate class images or generate the classification dataset that I've just showed you by clicking on this button, but you're not obligated to do that. As I said, the classification dataset will be created automatically once you start the training process. So that's it. Now feel free to click on Start Training and the training will start. But as I said, I won't be doing that right now because it would take a lot of time, but I'll show you how to use the resulted checkpoint to generate images. One last tip I want to mention. If you go to Settings, you have LoRA or Use LoRA option. And as I said, using this option, it would generate a LoRA file that wouldn't work, but also it would generate a Stable Diffusion checkpoint, which I think has the LoRA or the trained LoRA embedded within it. And when I tried generating images using that checkpoint, it worked fine and it generated great images. So it was trained using the LoRA technique, so it took much less time than training Dreambooth without LoRA. And it generated a checkpoint, so I think that's a great way to create custom Stable Diffusion checkpoints. And I'll show you afterwards that the generated images using this technique are great and works pretty well with different styles. But let me show you now how to generate a simple image using the trained Dreambooth checkpoint. So in case in a future version of the Dreambooth extension and the web UI itself, the LoRA would work correctly, and to find the LoRA or the trained LoRA files, you can simply find them in this folder called LoRAs. And to be able to use them within the user interface, you should copy those files and paste them within the LoRA folder, but the trained Dreambooth would be added automatically to the Stable Diffusion folder, so you can use it right away after training in the user interface. And as you can see here, if you trained Dreambooth using LoRA, a Stable Diffusion checkpoint would be added automatically, and as you can see here, the size is 4 gigabytes. So let's try to generate images of MLWH man, and as you can see, one recording it takes forever, so let me fast forward this part. Okay, so this is the result. I'm fine with it, we can improve it and I'll show you how to do it later on. Let's move on now to the last fine-tuning technique, which is LoRA. And to do that, you need to run the Koya SS GUI and then access the Dreambooth LoRA tab. And the first thing we need to do is to select the checkpoint or the Stable Diffusion checkpoint we're going to use to train LoRA. And you can use a custom checkpoint, and you can simply do that by clicking on this button and then selecting the checkpoint. So for example here, I will use the Dream Shaper. And then we move on to the next tab, which is the folders. And to train LoRA in the Koya SS GUI, we need to have a project with a specific folder structure, so I'll show you how to do that. So simply create a folder for your project. So for example here, I will call it LoRA tutorial, and within this folder, you need to create 3 folders. The first one for the images, the second one for the logging, and the third one for the models. So within the images folder, you can create multiple folders to train on multiple concepts. So in our case, we're only going to create one folder for one concept, which is MLWH. So the folder names here should have a specific format, which is the number of training steps per image, underscore the instance token. So for example, here we have 100 MLWH, and within this folder, you should copy the images with captions. And this time you need to make sure that the instance token is present in each caption. So once you do that, you can return to the user interface and copy each path in the correct text box. But before we do that, I will show you a quick way to set the training parameters. And as you can see, there are numerous training parameters, but the quickest way is to use a configuration file, and I will include a configuration file in the description so you can use it as well. This configuration file works well for low VRAM users, and you can load it from here. and it would set the different settings automatically. But then you can also tweak a little bit the settings, for example the train batch size if you have higher VRAM, the learning rate, and the different settings for low VRAM. But then when using this configuration file, it would set the image folder paths and the output and the logging folder paths automatically, and that's why you should load the configuration file before copying the paths. Otherwise you need to recopy and repaste the different paths. So now you simply copy the path for the images folder, for the logging folder, and for the output folder. And once you've done that, you simply need to choose a name for the output model, which will be the name for the generated LoRa file, and simply click on Train Model. So the training for LoRa would be very fast, less than 1 hour in my current configuration and my current settings with 31 training images. And to find the generated LoRa file, you can simply access the output folder that you've created, and there you can find the different checkpoints saved during the training process. And to use them within the Auto 1111 web UI, you simply copy the LoRa checkpoint that you want to use and paste it in the LoRa folder within the models directory, in the Auto 1111 directory of course. And then you can access them within the web UI the same way we did for the Hypernetworks, but now you can find the LoRa tab and you can refresh it if you want, and you can click on the LoRa you want to use. So now let's generate a simple image using our trained LoRa. And as you can see, this method generated the best result using this simple prompt. Alright, so this is the best result generated up to this point, and that's great. Let's now make some changes to the prompts and compare the different results that we can produce. So my advice, if you want to compare different methods or different checkpoints, is to use a good prompt with the same settings and the same seed, and to generate the images and compare them. So to find good prompts, for example in our case we've used the Dream Shaper. So from the Dream Shaper page in Civit AI, you can scroll here and select the images you like, and there you have the prompt and the different settings used to generate this image. You can copy the prompt and use the same settings. For the clip skip setting, you can find it within the settings tab of Stable Diffusion, and down here you can adjust the clip skip setting to 2, but I prefer the images with the clip skip set to 1. So before you click on generate, you need to adjust the prompt and insert your instance token, and if you're going to use a LoRa or a Hypernet, you should add it also to the prompt. So now we're going to use the trained LoRa. And also feel free to add some weight to the part where you mention the instance token, so that you produce images that resembles the object or the style you trained it on much more. Alright, that's a good result. It captured the style described in the prompt and kept the face recognizable. Let's try to increase the size of the image and modify the parameters a little bit. That's the next one, okay. So as you've seen, the generation process is very slow, and generating images while I'm recording takes forever. So I've prepared numerous images generated using the same settings and the same prompt to compare the different methods. And here are the results. I think this way you can better decide which method you prefer and which one is more suitable for your use case. In my opinion, after generating multiple images, I'm convinced that LoRa's are the best option, taken into consideration all the factors, from training time to image quality. They also have a higher degree of fidelity to the different features of the object trained on, and to the prompt as well. So overall I would go for LoRa's. The only issue with LoRa's is their tendencies to generate images in similar style of the training image. So for example, if you used only portrait images in the training process, as we did, the trained LoRa would tend to generate portrait images, even if you specifically state in the prompt that you want, for example, some wide-angle images or some zoomed-out images. And sometimes it's hard to get them to produce images in other style. But the remedy for that is to use, for example, ControlNet or InPainting to insert, for example, in this case, your face within other images that were generated using the same prompt. So for example, in these results, the images in the Star Wars style are generated using ControlNet on high resolution images of Star Wars characters. And as you can see, you can produce great results using these techniques. I will maybe make a video on how to use ControlNet and inpainting along with LoRa's and the other techniques in another video. So that's it for this video. I hope that you found this guide helpful in any way, and see you the next time.